Okay, this is the third and final hour for Physics 1C for November 8th, and we are going to be starting to talk about what's called electromagnetic induction. So what we have learned so far in this course is we've learned about electricity. We know how electric current can flow. We know what electric charges are that actually compose the current, and we understand the forces that are produced on them. And we then shifted into talking about magnetism, where we discussed how you can have a magnetic field produced by a current-carrying wire. And we also talked about the magnetic forces that are exerted on charged particles when they move near magnetic fields, as well as the magnetic forces that are placed on current-carrying wires. So we've seen that there is a lot of close-knit connections between electricity and magnetism. Electromagnetic induction is kind of the last piece of the puzzle that effectively ties everything together, because, as I said, we just learned about how electric currents can produce magnetic fields. So a natural thing to ask is, can you go the other way, right? We know that if I have an electric current I, it produces a magnetic field, right? So the question is, can I take a magnetic field and produce an electric current? Okay? We know we can do this, right? We have the example of the long current carrying wire. We have the example of the loop of wire. We have the example of the solenoid. I didn't mention it, but you can also do a magnetic field for a toroidal solenoid. So we know we can do all of these things. We know from electric current we can produce magnetism. Can we take magnetism and produce electric current? And the answer is yes. And the way we can do it is through something that's called electromagnetic induction. Okay. I really think the easiest way to describe this or to show you this is to just use one of the examples from the PhET website, because like normally what I would do is I would just set up a demo to show you how this works. So the easiest thing to do, of course, is just come here and use this as our version of a demo, since, you know, we're not really on campus, in spite of the fact that the world's mostly returned to normal. Which one are we going to use? Faraday's Law? I guess this one's fine. I don't know how good this one is, but it should be okay. Definitely used this one before. Okay, so here's what we have. We have a coil, sometimes called a pickup coil, right here. So coils of wire. You can see that these wires form, if you follow this, there is a closed circuit here. Okay. And that closed circuit is connected to a light bulb. Right? But as it is, there is no source of EMF, right? There's no way that you can get the light bulb to light up unless we connect a battery up here, or we connect a generator up here, or we connect a power supply or something like that. Except that if we take our magnet right here and we move it into this region where the coils are here, we notice that, oh my god, there's sounds on this one. Okay, I don't know if you could even hear those sounds. Were you all able to hear the sounds at all? Probably not, regardless. So now look what happens when we take the magnet and we move it in, and we move it out, move it in, we move it out. What we find is that by moving the magnet in and out here, this is a pretty bad, the way that they've done this is actually really bad, but whatever. It should be the case that the brightness goes up when I do this, but they actually have it so that the slower you move it, the bigger the brightness is. Whatever. Simulation. Simulated reality, nothing like real reality. Regardless, the point is that if I was to move this really quickly, the light would get really bright. Okay? Now, we can also throw a voltmeter in here, which is actually more relevant. And we can see what happens here. So here's our voltage. It can be positive, it can be negative. Okay? Notice what happens. When I pull the magnet out, it swings to the right, but when I push the magnet in, it swings to the left. And actually, the voltmeter may actually be doing this properly. I think it is, actually. Because the voltmeter, depending on how fast that I do this, you get a bigger deflection, right? Big deflection. Big deflection. But if we go slowly, the deflection is really quite small. And this is the important thing, as soon as you stop moving the magnet, there's no longer electricity being generated. So unlike our wires, where as long as I have a current, there is going to be a magnetic field, this one requires change. It is the change in the location of the magnetic field relative to the wire that is causing the EMF to happen, right? But nonetheless, you can see that there's an EMF that's occurring here. And I don't even need to actually put the magnet inside of there, but you'll notice that when I put the magnet out here and do the same thing, the light bulb isn't getting quite as bright. That's actually correct. And if I go really far away up here, like here, you can see that the needle is still moving, but it's moving very weakly. And that's because if I throw the field lines on here, the magnetic field lines are so much weaker, right? Remember that the strength of the magnetic field is the place where the lines are the closest together. And the place in this picture where the lines are the closest together is here. So in this region down here, the magnetic field, for one thing, it isn't actually changing very much. Whereas if I come here, you can see that there's all of these magnetic field lines. And when those field lines cross through the loop, that's when the big voltage happens, is when you get a really high density of field lines passing through the loop. We're going to find out that it's the flux, it's the change in flux that's key here. Now, can we rotate this? Okay, that's another thing we can do. Just by switching the direction of the magnet, that also has the same effect of pushing the magnet in and out. One other thing to note here, that's what a generator is, right? Yeah, basically. There actually is a... I have to do this. One of these has a generator. One of these is actually better, I think. This is better. Okay, let's finish looking at what we can with this one, though. We can also put a secondary loop in here. And, you know, that does whatever. Nothing too exciting. Let's look at this one. Browser compatible version. Learn more. What I'm going to show you now, Evan, is a little closer to what's going on with the generator. Assuming that actually loads up. Let's see if it loads up or not. Doesn't seem like it's going to load. Oh, graphics system is initializing. Okay, so bar magnet. This just shows field lines. Nothing exciting there. Pickup coil. So here, this one works way better. Because with this one, if you go really slowly, like this, you can see that the light bulb doesn't light up as much. But if you go fast, you get really fast. And the faster you go, basically, the brighter that it gets. Okay, that's kind of cool. Can do the same thing here with the voltage. Going in, it goes negative. Going out, it goes positive. We can flip the polarity and show that when I go in now, it goes positive, and when I go out, it goes negative. I'll flip it around to show you what was happening there. So what direction does it go when I go this way? It goes negative. When I pull out, it goes positive. When I flip polarity around, south in first, it goes positive. South in out, it goes negative, right? All right. What else can we do? We can increase the number of loops here. And now what happens when we increase the number of loops is that the amount of voltage that we're getting is bigger. So it looks like the number of loops is directly proportional to the size of the voltage increase here. We can also make the magnet stronger, which will help as well. Okay. We can increase the area of the loops to make the area of the loops bigger. And again, this will also have a positive impact on how much EMF we generate here. See how it's very easily hitting the top end there? Whereas if we make the loop smaller and do the same thing, yeah, it's pretty much the same. And again, it's still a simulation, so it's not going to be 100% accurate. So that is basically Faraday's law of induction in action. The motion of a magnet, right? The motion of a magnet near a coil can generate electricity. This is at the core of how all electricity is generated all across the world. And here's a generator, which has an example of how this works. So in a hydroelectric dam, what you have is you have water that falls over a spillway, right? or sorry, water that falls through a spillway and then over turbines. In this case, the turbine is directly connected to a magnet. So the magnet now starts to rotate. And you can see now that, here we'll use this version. As that magnet rotates near my coil right here, it's going to create a changing electric flux. And as a result, we're going to get an EMF. We call this an alternating current, actually, that's coming out of here. Because as you can see, sometimes it goes down and then up and then down and then up and then down and then up. That's an alternating current, right? If we increase the number of loops again, now the effect is even bigger. We go to 4. No, we can't. We go down to 1. See, it's not oscillating as much. So the number of loops is, the more loops you can get, the better. Loop area going up, you're going to get a bigger influence too. See if we make the loop smaller. I don't think it's showing as much in this case. It kind of is. Kind of is. We can make the thing move faster. We can make the this go faster by just increasing the speed of the water here. You can see that has a direct impact on how strong the electricity that we get out of this is. Anyway, then of course we can make the magnet itself stronger, which again will also massively increase the electricity we're generating. So there you go, Evan. This is your generator, basically. A very simplistic kind of generator, but a generator nonetheless. You could also reverse the process, meaning one other thing you could do is instead of having the magnet be the thing that's rotating, you could have the wires be the thing that's rotating and have the magnet sit still, and the exact same thing would happen. Okay. Let's see. We also have this one. This one's really cool. So for me, this is such a sad day for me to be sitting here showing you Faraday's Law of Induction with just a simulation, because this is, I remember the first time that I saw this, I was really blown away by the fact that just moving a magnet near a coil of wire, that you could get this electricity here. And immediately what I started thinking about when I first saw this was wireless devices. A lot of wireless devices use this idea to pass electricity from one object to another. Mr. User Account says, it ends up alternating between the same voltage just like negative and positive, right? Because when you had the previous simulation, you left the magnet, it just returned to its center, but here it's going back and forth. Here. Yeah, the key thing here is that this one never stops moving, right? This one never stops moving. Because this one never stops moving, it's always going to be positive, negative, but when we come back to here, when I'm not moving it, there is no induced current. We call this induced current. When I move it, there's induced current. When I don't move it, nothing happens. Nothing happens. Okay, so to take things to an even higher level, this is really cool. So here we have a battery that is constructed into the form of an electromagnet by these wires right here, right? You can see the magnetic fields that are produced, right? And it turns out that this can also act like a magnet. I mean, it creates a magnetic field, so it should act like a magnet, right? So now we can actually induce current. There's current flowing in this device, right? And I can make current flow in another device. This is how things like all the wireless charging stuff that exists now works off of this principle. It works off this principle. Now, there's a problem here, though, which is that in order to make this happen, I have to actually move my electromagnet, right? But we can fix that by switching from direct current to alternating current. So watch what happens now. If I switch this to alternating current here, now the current is going to flow up and then down and up and then down. And what's going to happen is, here, I'll go back here to show you what's going to happen before I do it. Here, notice that I was saying that if I flip my polarity, if I'm just constantly flipping my polarity, you get an EMF, right? But we could do the exact same thing by making the current flow up and then down and then up and then down, right? So the way we do that is just to switch to AC. So now we have an AC current supply, and it's now directly inducing a current in the other thing pretty much constantly. And we could, of course, amp that up if we just increase some things here. One thing that we can do is we can see what happens if we increase the size of the current. What happened? I'll go back to 50. Or I guess, what would you predict would happen here? Do you think the light bulb is going to get brighter if we make the current have wider amplitudes, meaning more current? That seems reasonable, right? Make this bigger, light bulb gets brighter, right? The other thing we can do is we can increase the frequency down here. If we make it go really fast, now the light bulb is getting even brighter. So there's a lot of things that go into this. There are the number of loops, there's the area of the loop, there's the size of the magnetic field that's being produced, and there's the rate of change. All four of those things go into producing this effect that we call electromagnetic induction, which really is quite fascinating. The way that an electric toothbrush charges, or the way that if you have like a wireless charging pad for your phone, it works exactly off of this principle here. It works exactly off this principle. A wireless transfer of energy, a wireless transfer of electrical energy that requires no contacts at all, which is really powerful. So let's talk about the physics of this. So we call this electromagnetic induction, okay? And the thing to talk about now is what makes this happen, okay? So experiments show, like the ones that I was just showing you, that moving a magnet near or through a coil of wire will cause what we call an induced current. That's why we call it induction. We call this process induction in the coil. And the factors that affect this are: one, the size of the magnetic fields. Two, the area of the coil. Three, the angle between the plane of the coil and the magnetic fields. And basically, if any of these three things change, then you're going to get an induced current. If the size of the field changes, you're going to get an induced current. If the area of the coil changes, you're going to get an induced current. If the angle between the plane of the coil and the magnetic field changes, you're going to get an induced current. But there has to be change. This will not happen if there is no change. We take those things together, magnetic field, area of the coil, and the plane of the coil and the magnetic field. And I guess really what I should be doing here is I should draw a situation. Suppose that I have a magnetic field that looks like this. Suppose that in a region of space I have a magnetic field that looks like this, right? And I take a coil, right? And I take my coil here. And let's say that I take my coil like this. So I've got a coil right here, some radius r, right? And say that I take my coil and I move it into the magnetic field like this. So I move it this direction. What's going to happen is that it's going to induce a current within the coil. Okay, and the way that it's going to induce it is going to be, well, I don't know if it matters, but I'll teach you how to figure this out. This way. This is going to be the direction of what we call the induced current, so I'll call it I and D. That looks awful. I with a little subscript I in D. Call that the induced current. Likewise, if I take my coil and I place it here, and I tell you that the area vector for my coil points this way, if I now twist it like this, so if I rotate the coil, so rotation of the coil will also lead to an induced current in the coil. In addition to that, if I were to take a loop of wire like this, okay, and I take that wire and I pull in both directions this way, so I pull on both sides so that the wire drops to an area of 0, then the area of the coil would change, and that would also lead to an induced current. So those three things, if the size of the magnetic field changes, as in if you go from a magnetic field here that's equal to 0 to a magnetic field that's equal to something, you push the coil inside the magnetic field, that'll lead to induced current. The area of the coil changing will lead to induced current, and the angle between the plane of the coil and the magnetic field will lead to induced current. And if you are remembering how all these things interact with each other, you might notice that when I take magnetic field B, area A, and the angle between the plane and the coil of the magnetic field, you might remember that all those things are contained together in a concept that's called magnetic flux, where magnetic flux is defined as B dot dA integral, or in very simple cases, if it's a constant magnetic field, the magnetic flux might just be something like, B times A times the cosine of the angle theta. So electromagnetic induction occurs when magnetic flux changes. That's how we can summarize all of these concepts here. So to summarize that, we can say that electromagnetic induction occurs when the magnetic flux through a closed loop, it has to be a closed loop, or coil, changes. Any change in magnetic flux will lead to electromagnetic induction. And the faster the flux changes, the bigger the induction is going to be. And we can state that as an equation, which we call Faraday's law of induction, or just simply Faraday's law. That's what we're going to call it, Faraday's law. That's what we're going to call it, but it's Faraday's law of induction. Okay. So anytime there is a change in magnetic flux with respect to time, so when there's a change in magnetic flux, this will produce an EMF. We call it an induced EMF, so I'll put E with an I and D down here to stand for induced. And there's going to be a negative sign in front of this, and the other thing that's going to be in front of this is going to be the number of turns of wire you have. So the induced EMF in a wire is given by negative N times d phi dt, where phi is the flux. This is the last Maxwell equation. This is the fourth and final Maxwell equation. We have them all now. Gauss's law, Ampere's law, and Faraday's law. Those are the Maxwell equations. And this is probably the simplest of all of them, because it has a derivative instead of an integral. Although I am kind of lying to you, because technically the full form of this law looks like this. This is the full form of this law. But, I mean, there are a few problems where you have to use this version, but most of the time we're just going to be using this version here. And that's Faraday's law of induction. Technically, at this point, you know almost everything there is to know about the way in which electrical and magnetic systems operate, at least at their core, at least the most fundamental concepts about how they operate. Of course, we're not really going to understand this unless we look at some problems and see how it's used in practice, so let's do that. Do a couple of examples here. Okay, so here we have the EMF and current induced in a loop. Notice this is EMF, by the way, not current. To get current, you're going to have to divide by resistance. All right, it says the magnetic field between the poles of an electromagnet in 29.5 is uniform at any time, but its magnitude is increasing at a rate of 0.02 teslas per second. The area of the conducting loop in the field is 120 centimeters squared, and the total circuit resistance, including the meter, is 5 ohms. Find the induced EMF and the induced current in the circuit. If the loop is replaced by one made of an insulator, what effect does this have on the induced EMF and the induced current? This is a relatively straightforward Faraday's Law problem. So here's what we know. We're given that we have this magnet here. We have a loop of wire. The area of the loop of the wire, which is just the area of the loop itself, not the whole area of the magnet, okay? The area of the loop is 0.012 meters squared. It says centimeter. They've already converted it here for us. We also know the resistance of our system is equal to 5 ohms, and we know that the magnetic field between these two pieces here is increasing at a rate of 0.020 teslas per second. So we're going to call that dB/dt, the rate at which the magnetic field is increasing. If we were taking physics 2b, we would call this delta B over delta T. Okay. So the first thing we want to do, A, is to find the induced EMF, and we also want to find the current flowing through the wire. Okay. So to find the induced EMF, we're going to use Faraday's law of induction, negative N d phi dt. By the way, I didn't tell you why there's a negative sign there, did I? We'll talk about that as we go through this. So this is going to be E induced is equal to, there's only one loop of wire, right? It says it's just one conducting loop, yeah. So this is going to be negative 1 times d phi dt. So that's going to be d dt of b times a times the cosine of the angle between b and a. So this is going to be equal to negative 1. Now, the area of the loop doesn't change, and the angle theta here, we're just going to say is equal to 0, because you can see that the area of the loop points this way, and the magnetic field points in the same direction. So theta is going to be 0. So we're just going to have negative 1 multiplied by the area, and then multiplied by dB dt. And this is going to give us negative 1. The area was 0.012 meters squared, and then dB dt is 0.02 teslas per second. That's the induced EMF. So our induced EMF in this case is going to be 1, 2, 3. Something like this. Is that right? You all tell me. Is it negative 4? Yeah, it's negative 4. I agree. Okay. So a very small amount of EMF, but the rate of change here isn't very high, and the area of the loop is kind of low. You can see that as the area of the loop goes up, the EMF induced gets bigger, and as the rate at which the magnetic field is changing goes up, it also gets bigger. Okay, any questions about that? One thing I want to emphasize, and I don't know how explicit the book is about this, is that oh, there's a negative sign too, that's right. Okay. So that negative sign, as we're going to find out, is really not that important. It's more about, I want to mention one other thing here, which is, suppose that our loop, okay, was bigger than the magnetic field, right? Suppose this was our loop, right? Then if we were to look at that from overhead, what that would look like is we'd have this big loop like this, right? This would be our loop of wire. And if the magnetic field only existed in this little region right here, that's the magnetic field coming out like that, then the area that you would use would be this area here, the inner area. All of this region out here would not count. I don't know that the book ever says that, but it's true. So in our problem here, our loop was smaller than the size of the magnetic field, right? But what I'm saying is if the loop was bigger than the magnetic field, you would just use the region where there is magnetic flux. Does that make sense? All right. Now, what does the negative sign mean? The negative sign means that if you were to point your fingers in the direction of the magnetic field, then your fingers would sweep around kind of in this direction here. The negative sign tells you that the direction of the current is going to be opposite to that. So when the magnetic field points this way and your fingers sweep this way, the negative sign tells you that you have to kind of flip your thumb around like this to find the direction of the induced current. So the induced current in this case flows this way. And we're going to get more into that here as we go along. But that's what the negative sign tells you. It tells you that when the flux is increasing, the direction of the induced EMF is opposite to the direction of the external magnetic fields. When the magnetic flux is decreasing, the direction of the induced EMF is in the same direction as the magnetic field. So you can see very clearly, right, that if dB/dt here had been a negative number, our answer would have been positive, right? So if the magnetic field was decreasing, the direction of the induced current would have been opposite to what it is here. All right. If you're confused by that, that's okay. We're going to talk more about it here in a little bit. For now, let's just focus on how we actually calculate the induced EMF. All right. So next is we want to find the induced EMF and the induced current. To find the induced current, this is really quite easy to do. All we need to do is to take our induced EMF, and we're going to divide by the resistance. I'm going to find just the magnitude of the induced current. I don't really care about this negative sign here for now. So now all we're going to do is take 2.4 times 10 to the minus 4 volts and divide by the resistance, which is 5. Let's see, 2.4 divided by 5 is going to be like dividing by 10 and multiplying by 2. So it's 0.24 multiplied by 2 would be 0.48. So I think it's going to be 4.8 times 10 to the negative 5. Maybe. Does that seem right? No. Yes. I think that's right. You all agree? It's kind of off the screen a little bit, and my units are wrong, so I'll fix those. This should have been amps. So far so good. Hopefully, should be pretty easy to understand this. This is some really basic Faraday's Law stuff. Okay. Next, in part B, it says, if the loop was replaced by one made of an insulator, so instead of a conductor, an insulator, what effect does this have on the induced EMF and the induced current? Well, for part B, the induced EMF will be unchanged. Okay. However, the induced current should be negligibly small. The induced current should be approximately 0 because for an insulator, R is going to be much, much greater than, it's just going to be big. The resistance will be big. So it's important to understand that there can be an induced EMF even if there isn't a current that's produced from that. The induced EMF will still be there. All right. Does that make sense? All right. So the next thing that I would want to talk about is how do we make sense of this direction thing? How do we make sense of this direction thing? And to do that, we use something that is called Lenz's law. I would say the coolest demos we have involve Lenz's law. I have to show you some of these this week. I hope I have time. So Lenz's law answers the question, what is the direction of the induced current? And the answer is quite complicated, but I'll give you some ways to understand it. So Lenz's law states that the direction of the induced current is such to oppose the change. That's pretty much what it says. It's the simplest way that I can write it down. There's a lot more to it, but I'm going to write it down like that. The direction of the induced current opposes, I have to put another word in here. The direction of the induced current has an induced magnetic field which opposes the change in magnetic flux. Okay, that's what Lenz's law says. It says the direction of the induced current has an induced magnetic field which opposes the change in magnetic flux. So this picture's pretty good, but let me give you some examples first of how you do this. All right. So let's say that I have a loop of wire, okay? So this is just a loop of wire. And let's say that we're looking at it edge on. So what I mean by that is that, so this would be a loop of wire that we're looking at kind of flat, and we're looking at it kind of on its edge. So we see it as an angle like that. In fact, I could probably do you a little bit better here and actually use one of these things here. So we're looking at a loop of wire that kind of looks like this, okay? And what we're going to do is we're going to drop a magnet through it, okay? So we're going to take the north end of a magnet here. This is the north end of our magnet. This is the south end of our magnet, and we're just going to drop it. And we're going to try to figure out what in the hell Lenz's law means, okay? Now, the first thing I'm going to do to make this as simple as I possibly can is we're going to simplify the magnetic field that's produced by this object and just say that it points down, okay? That's our external magnetic field right there, all right? Now, by dropping the magnet through the coil, we know there's going to be an induced current. It is either going to point to the right in the front, or it is going to point to the left in the front, right? So here's what you do. First, you ask yourself the following question. Is flux increasing or decreasing? What do you think in this case? The flux through my coil, is the magnetic flux increasing or decreasing? Are there more or less field lines that are going to be flowing through this? It's increasing, okay? So when you have increasing, here's what you do. Point your thumb opposite to the external field. Okay? So the external field is down, right? So so flip it, basically. Flip your thumb upside down, okay? So do that with me. Point your thumb this way, okay? Point your thumb opposite to the external field. This is the direction of what I'm going to call B induced. The induced magnetic field. Okay? So that means that the induced magnetic field in my wire now is going to be pointing this way. Okay, let's use a different color. Let's use this color. My induced magnetic field goes this way now, okay? I'm going to draw it on my picture, right? And now what you do is you use the right-hand rule. If my induced magnetic field goes this way, the type of current that would produce such a magnetic field would swing and wrap around this way, so I know that my induced current must be going like this. Remember, this is the front, and this is the back here, okay? The current's going to come around the front and then go around the back like that, okay? So again, to follow this up, because the flux is increasing, I look at the direction of the external field and I flip it. That direction is the direction of my induced magnetic field, and you go backwards from that to figure out what kind of a current would produce such an induced magnetic field, and it would be the type of current that flows around like this. So that must be the direction of the induced current. You all understand? It's really quite complicated, but it's also something that you can learn. And I think once you get it, it's really not that hard. Let's look at these words here and see if it actually makes any sense. The words of Lenz's law state that the direction of the induced current has an induced magnetic field which opposes the change in magnetic flux. So in this case, the magnetic flux was increasing down, increasing magnetic flux downwards. So we need to flip our thumb up and say that's going to be the direction of the induced magnetic field. Okay? Does everyone understand? So the other possibility is if the flux is decreasing. When the flux is decreasing, you're going to point your thumb in the same direction as the external magnetic fields, and this will be the direction of the induced magnetic field. I'll give you an example of this, of course. And then step 2, so step 1, this is step 1A, this is step 1B. They're separate from each other. Step 2 is to use the right-hand rule, RHR's right-hand rule, to determine direction of induced current. And that is how you do Lenz's law. That's how you do it. Okay? Let me give you a decreasing example, all right? So we take a loop, okay? And now let's consider what happens after our magnet has fallen through the loop, okay? So basically the same loop as we had before, but now what we're going to be doing is we're going to say, suppose that our magnet has now fallen past the loop. Let's now find the direction of our induced current. Okay? So the magnet is falling still, falling magnet. So it's moving, right? And again, the easiest thing to do here is to just draw a line like this to represent your external magnetic field. Be external like that. Then you ask the first question, is the flux increasing or decreasing? What do you think? Is the flux increasing or decreasing in this case? It's decreasing. When the flux decreases, we look at this rule right here. Point your thumb in the same direction as the external magnetic field. This is the direction of B induced. Okay, so B external is this way, B induced, same direction, right? So let's draw that on our picture here. So this is going to be B induced. I'm just going to write over here on the left. This was, we said, increasing flux, and this one's going to be the decreasing flux example. Okay, so B induced points in that direction, and now we just point our thumb that way, swing our fingers around. That's the direction of the current. So now the direction of the induced current in this case goes this way, opposite. Does it make sense? It's kind of tricky. But the more you do it, the easier it gets. The more examples you see, the easier it gets. And that's really all there is to it, okay? So Lenz's law, the direction of the induced current has an induced magnetic field which opposes the change in magnetic flux. That's a lot of words. This would actually produce, it wouldn't actually produce AC current. It would actually, the current would kind of like go up like this and then switch and change, but it's basic. It's similar to AC current. It's not exactly like what we call AC current, but it's kind of like it. It's kind of similar. The actual profile of what this looks like in terms of the current, if you plotted the current as a function of time, in this case, I think it looks something like this. I think it goes like no current, and then it spikes, and then it switches, and then it does that. So it is kind of like AC current, but more like a pulse, because alternating current has to continue, right? But this is like a pulse kind of thing. Okay, so let's now look at their picture. Now that we've drawn it ourselves and we've thought about it, because now we can look at this picture and try to understand something about what's happening here. And hopefully I can... there's not enough time. I probably should have skipped Lenz's law and I should have done this, but whatever. I might spend 5 minutes doing motional EMF at the end. I don't know. We'll see. So here's our picture that they have in the book, which is all kinds of things going on, but the same as what we just did, right? So here we have the motion of a magnet causes an increasing downward flux through the loop, right? Magnet moves down. You notice that the external magnetic field points downwards here. This is the thing I hate about this. Like, yes, here's your magnetic field lines, but like they could really simplify this by saying that's your external field, right? Regardless, doesn't really matter. Magnetic field lines, all those magnetic field lines are going through our loop. The flux is increasing because this is the region where the magnetic field is the strongest. So we say the magnetic field that's induced has to point opposite to that, and then as a result, the current is going to flow around the front right here. You can pull the magnet. See, this is so confusing. Let's go from A to C, okay? Because they flipped the direction of the magnet here on us. If we go from A to C, in C it's the same magnet, same shape, except now the magnet's moving up. Because the magnet moves up, the magnetic flux is decreasing, which means the induced magnetic field needs to point in the same direction as the external magnetic field, and then the current goes that way. You can look at C and D, B and D for yourself if you want to. In this case, the upward motion of the magnet is a decreasing upward flux, so the induced magnetic field needs to point in the same direction. And in case D, when the magnet goes in, it's an increasing upward flux. Oh, right, because the magnetic field in this case, this is why I hate these pictures. They only show half the magnetic field too. The magnetic field in this place goes this way, so when the magnetic field falls in, it's increasing upward flux, and so you flip your finger this way and you get the induced magnetic field. God, I hate this textbook so much. Anyway, so I'm going to go over a little bit here, and I apologize. We spent a lot of time at the beginning of class talking about like last days of drop and stuff, so I think this is fair. If you need to go, if you have another class or something like that, feel free to go. I feel like it would be kind of weak if I didn't show you this last part here. So let's talk about motional EMF real quick. This is really fast, but it's also going to be really useful to your homework. So consider the following scenario. Suppose that I have a set of wires that are connected like this. I have wires that are shaped like a U, like this. All right. So I have a long wire bent in the shape of a U. There's my wire, okay? And let's say that my wire has a resistance. Let's give it some resistance. And let's say that this represents pretty much the total resistance of my wire. Let's say that almost all of the resistance is included in this little piece right here. But nonetheless, I have a continuous wire like this, all right? I lay on top of my wire something that is available to slide. So another piece of metal is laid along here on top of my wire, but it makes electrical contacts right here and right here, okay? So I put a bar on top of here that's also a metal, so this is a metal bar, and it makes electrical contacts there and there, right? The next thing that I'm gonna do is we're going to place an external magnetic field existing in this region right here. So all throughout this region here, and continuing on forever basically, or as far as we need, there's going to be a magnetic field that points into the page. So that's my magnetic field right there. What else do we need to know? We're also going to need to know the length between this point and this point. We're going to call that L. And now here's what we're going to do. We're going to pull the bar to the right. So, or we're going to make the bar move with a constant speed in this direction here. Let's use a different color. We're going to make the bar move in this direction with a constant velocity. So v is going to be equal to constant. And of course, this is only going to happen if we're pulling on it, right? So basically, we are pulling with some kind of a force in this direction. We're going to call it my applied force, okay? And we're pulling in such a way that the velocity is constant for the bar, okay? Now, you all tell me, I have a closed circuit right here, basically between these points. That's a closed circuit, right? And as the wire moves to the right, what happens to the magnetic flux through this region right here? Is it increasing or decreasing? It's increasing, right? Okay. So increase in flux. You all tell me, what is the direction of the induced current going to be? Along, let's say, this wire right here. Should it point up or down? My current through this portion of the wire here, is it going to go up or is it going to go down? Increase in flux. So we have to look at the direction of the external field, which is in, right? When it's an increase, we switch our thumb this way, right? And then we just wrap our fingers around this way. So what direction is the electric current flowing through this piece right here going to be? Up or down? I want everyone, or as many people as are still here, to go ahead and guess. You all just agree with each other? Well, you're all wrong. It's up. Why is it up? Okay, it's an increase in flux, right? So that means that B induced, the induced magnetic field, is opposite to B, right? So I'm going to draw it inside of here. If B points that way, B induced has to point this way, right? And if you have an induced magnetic field that points that way, it's going to wrap and swing around and produce a counterclockwise current. So my current here is going to flow this way, just like that, okay? Do you all agree? Now I draw it that way? I totally understand that you wouldn't get it right, and we just learned this, so it's understandable. So we know the direction of the current, right? Okay, the next question is, what is the induced EMF in this case? And this is actually quite easy to do. In order to do this, what we're going to do is we're going to say, label this side right here to be X, okay? Then I can say that my magnetic flux in this case, phi B, which is equal to B times A, should be equal to B times L times X, right? That's my magnetic flux. Then if I do EMF is going to be equal to negative the derivative of BLX. If I do negative ddt of BLX, then what I'm going to get is that B and L are constant, so I'll have B, L, and then dx dt, right? And dx dt is just going to be the velocity. And that is going to be my EMF. I'm just going to talk about the absolute value because I don't really care about the negative sign. The negative sign is just a way to describe that the direction goes that way. We're stopping right there. We covered it. You can read more about it in your textbook if you want to. I don't want to go very much over. We'll start with motional EMF next time, but unless I'm crazy, I think that's most of chapter 29. Unless I'm crazy. I'm pretty sure, well, there's also displacement current, but that's you should be able to do most of your homework now with this section. It's actually kind of a short chapter. All right, that's everything for today. I hope you all have a great night, and I will see you on Wednesday if you're in the first half of the alphabet, and we're going to do lab E-11, okay? Everyone have a nice night, and I will see you later. Function shift.